Alright, so today we are finishing off our discussion of Lie algebras, I think, just as a whole, and we're starting off with variation of admissible lattice. I'm going to let V be V lambda, be an irreducible L module. I want to know what the possible choices of admissible lattices is in V. We know an admissible lattice must contain a maximal vector V plus and hence must include the admissible lattice UZ minus acting on V plus, which is equivalent to UZ acting on V plus by a previous proof. Since our V plus is uniquely determined by V, up to a scalar multiple, we can fix a V plus at discussion and denote the minimal admissible lattice UZ of V plus by M min. I'm being a little inconsistent with how I'm writing my Z's. Now we want to know which other admissible lattices intersect V lambda in Z of V plus. So I don't need to scroll quite yet. So we're going to recall the definition of a dual or contragradient module. V star is the vector space dual of L of V with L acting by the rule X on F acting on a W is negative F of X acting on a W, where of course X is an element over L acting on F being a function on a linear function on V, so it's in V star, with W being the ultimate subject in V. If X is a subspace of V star invariant, which is invariant under L, then the corresponding subspace, corresponding subspace X perpendicular of V is going to be invariant under L. So V star is again irreducible. We can specify its highest weight. Let's sigma in the file group send our base to the negative base, so it sends our root system, if phi is the root system, it sends phi plus to phi minus. And let wv be a non-zero vector of weight of sigma lambda. So W is a minimal vector in the sense that you'll see it's killed by all x to the negative alpha as the dimension of v sigma lambda we saw as the dimension of v lambda is 1. W is essentially unique. Relative to a basis of V consisting of W and other weight vectors. We can take f plus to be the linear function dual to W. Then f plus is a maximal vector of V star of weight negative sigma lambda and V star is isomorphic to V negative sigma lambda. Now we let M be an admissible lattice in V. We define M star to be the set of functions, vectors in V star, where f of M, the image of M is integers. If M is the Z span of a certain basis of V, then M star is the integer span of the dual basis. In particular, M star is a lattice, and is actually admissible. Well, for V and M, F and M star, x alpha to the M over M factorial acting on our function, then being applied to V gives you plus or minus f of x alpha to the M over M factorial acting on V, which is an integer. And we see that an inclusion of admissible lattices like this, admissible lattices induces a reverse inclusion where M1 star is now going to be include M2 star. Alright, now assume that V plus is fixed as above, and so M minimum is fixed. Then there is a canonical way to choose a minimal vector in the intersection of V sigma lambda and M minimum. And this is just from noticing that the eval reflections we constructed before are transformations of V. So we can take from previous reflections in the eval group from previous work we saw we can and these are going to be transformation of V representing elements of U of Z with, say, sigma mapping integer scales of V plus onto the intersection of M minimum and V sigma lambda. We may define W as the image of V plus, and then we can take F plus to be V star, V and V star negative sigma lambda as above. So from that we get pretty much immediately that the dual of M minimum intersecting the dual of V negative sigma lambda is the integer scale copies of F plus. Now we can let M be an admissible lattice in V intersecting V lambda precisely in ZV plus. Then we see by our previous argument here that M intersects V sigma lambda precisely in ZW. So M star intersects V negative sigma F star precisely in getting screwed up here. In Z of F plus. Now we can so as M varies over the collection of all the admissible lattices in V star, admissible lattices in V of the indicated type M star varies over the admissible lattices in V star with inclusions reversed. That shows that M star has upper and lower bounds, essentially. So M does as well. Alright. Leaves us, we can summarize this as an immediate proposition. Let V be V lambda, lambda in lambda plus, with maximal vector V plus. For A, each admissible intersecting V lambda in Z V plus includes M minimum, which is UZ on V plus, and each such admissible lattice intersecting V lambda in Z V star is included in M max, the lattice dual to a suitable M star min in V star. Okay, I want to check. Yes, this does appear. Okay. There's 2 more sections and then we are done with everything in algebra. So our next topic is passage to an arbitrary field. So we're going to let Fp be the prime field of characteristic P, of course, with K an extension field of Fp. I guess I should be writing the F blackboard or double stroke. I don't know what they call that. we're going to let V be a faithful L module. Then the weight of V span a lattice between our lambda r and lambda, which we denoted, we've already seen this, lambda of V. We want to choose an admissible lattice M in V with a stabilizer LV, which we recall as HV, plus the collection of Z copies of X alpha for alpha over a root system. And this is a stabilizer in L. And we're going to let HV be the collection of elements H and H with lambda H being an integer for all lambda in lambda V. So we're going to let V of k be the integer tensor of M with k. So just change the basis of M from the integers to k. And likewise LV of k be extending our LV through that integer tensor to k. Since LV is isomorphic, to a subgroup of the endomorphisms of M, and is closed into the bracket, of course. LVK may be identified with a Lie subalgebra of the general linear Lie group, Lie algebra, of our V of k, which is, of course, just our endomorphisms of V of k. Moreover, the inclusion L integers into LV induces a Lie algebra homomorphism LK into LV of k, which is injective on our collection of k scaling X alpha, but may have a non-zero kernel in the extension of H over Z to K, which is H of K. And so we can look at an example. Recall the discussion of SL2 of F. If our P there is 2, this was our previous discussion in the previous chapter, then H tensor 1 in LK is sent to So 2 times h over 2 tensor 1, which is going to be 0 in LV of k. In the adjoint representation, which is when v is equal to L. We also see that the multiplication in LK differs from that in LVK. For example, the bracket of h and x, we know is 2x, which is 0 in LK. But the bracket of h over 2 with x is non-zero in LVK. This is all in characteristic 2, mind you, so that's why all of our references to doubling things ends up turning them into 0. Now, when we're in characteristic not 2, also known as a well-behaved characteristic, this map from LK to LVK is an isomorphism. This is an isomorphism for either choice of weight lattice. And that's an exercise you can try to work through yourself. And thus we see each faithful L module V gives rise via the homomorphism from LK to LVK to a module V of k for LK, which may not be faithful. Namely, when LK has an ideal necessarily central included in H of k, and we note here all of this depends, in this case, on the choice of the admissible lattice M in V. Now we want the analog here of the Chevalier group GK from before. Since M is stable, under the endomorphism x alpha to the t over t factorial, which for our representation is going to be phi of x alpha to the t over t factorial. Vk is stable under the corresponding endomorphism, which we call x alpha of t. Notice that for t less than p, x alpha t acts like x alpha tensor 1 to the t over t factorial, whereas for t being greater than or equal to p, this notation is meaningless. As x alpha t is 0 for large enough t, we can write theta alpha of 1 as the sum of t from 0 to infinity of x alpha t being an endomorphism of v of k. As we see that theta alpha of 1 has determinant 1, it belongs to the special linear Lie group of v of k. Now, more generally, we can define an automorphism theta alpha c of v of k by forming the sum for t 0 to infinity of t of x alpha to our index t over t factorial, of course, and then specializing the indeterminate t to c in our k. The group GVK generated by all theta alpha of c for alpha across our root system and c across k is called a Chevalley group of type lambda v, and its adjoint f lambda v is lambda r, universal f lambda v is the other extreme, lambda. And as before, GV of k depends on our choice of m. Now this is actually going to be now our last section here, which is just kind of a survey of related results. So there's a bunch of kind of obvious branching points when you get to this kind of point in our work here. And so there's just some just gonna give you 4 different results here without really proving them at all or anything, just an overview of what kind of things you can do with this. First off, up to isomorphism, GV of k and LV of k depend on the weight lattice, lambda v, but not on our v itself or our choice of m. Although it will be noted, m affects the action of GVK and LVK on, well, V of k. If lambda v contains lambda w, there exists a canonical homomorphisms GV of k into GW of k and LW of k into LV of k. In particular, the Chevalier groups of universal type cover all others, and the Chevalier groups of the adjoint type are covered by all others. Part 2. Let V be V lambda for lambda in lambda plus, M be our M minimum. Then Vk, then Vk is a cyclic module. Sorry, I gotta reset this all up, restructure it. And Vk is a cyclic module for GV of k generated by a vector v tensor 1 for v in both m and v lambda. Thus Vk has a unique maximal GV of k submodule hence has a unique irreducible homomorphic image, which is of course going to be of highest weight lambda. On the other hand, if m is m max, then Vk has a unique irreducible submodule highest weight lambda. Number 3, when lambda in lambda plus satisfies lambda of hi being strictly non-negative and strictly less than p for all hi's, and where p is the characteristic of k, then the assertion in 2 holds for LV of k in place of GV of k. With the resulting p to the L irreducible modules are inequivalent and exhaust the isomorphism classes of the irreducible, restricted, LK modules. And finally, the composition factors of the K viewed as a module for either GVK or LVK are independent of the choice of admissible lattice. And with that, yeah, they've got some exercises, notes from where this is all sourced from, references to the book, and yeah, that's the end of Humphreys, it looks like, actually. So with that done, we're going back to Bourbaki and Serre, both of which I think we left off right as we're entering the discussion of Lie groups. So that will be the rest of this series, I guess. Yeah. We are officially done with our discussion of algebra as I know it. So that's exciting. Look forward till the group talk here tomorrow, hopefully. Thanks for watching.